Okay, so we're now looking at the section of the book that corresponds to 7E and 7F. So the idea is we're going to talk about cases that are not just equilibrium, okay? So we've previously considered smooth planes and rough planes, but we had things not moving. We had them about to move. So in this case, we have a particle is held at rest on a rough plane, so there's friction, which is inclined at an angle, and we've got one of these again where we don't get told the angle directly, but we've got a situation where alpha is opposite over adjacent, so 3/4. So we have to use this one here, and typically you use this one to get your sine alpha or cos alpha. So sine alpha in this case is opposite over hypotenuse. Okay, so we're going to use these instead of actually working out what an angle is. So the coefficient of friction is 0.5, okay? The particle is released. Well, that's why I actually underlined rest before, because what's probably going to happen is we're going to have some sort of Suvat scenario, and we're going to have something starting off at 0 and then developing some velocity as it goes down the slope, okay? Find the acceleration of the particle. Okay, so what's going on here? Well, a few things. So I've already said that we might have some Suvat, yeah? So how does that link to what we've been doing before? Well, Suvat, the only thing that really links to the force diagrams from before is the A value, right? And it links via F equals ma. So we're going to have force diagrams. We're going to have, interestingly, I can't see the mass on this one here. We're typically going to have the mass. So I guess I don't need that for this particular question. However, you will find for lots of questions, you'll need the mass, and forces using the mass gives you acceleration. So we're often going to be doing things like this. And sometimes we do F equals ma and then we get stuck with Suvat, or sometimes we actually do the reverse with that. Okay, so some of the questions are going to look a bit intimidating now because we're going to mix together lots of different ideas. We're going to have forces, possibly F equals ma, maybe Suvat, maybe everything mixed together. So it's not immediately obvious, but these are some things to look out for. Okay, so it's on a plane. Yes, I've got a block on a slope, haven't I? That's basically what's going on. And I don't know the mass, so I'm just going to guess at the moment that it's useful to write mg. I have R. It's held at rest. So it sounds to me like it's just this situation here, and then it's going to go down the slope. So we're also told that it's a rough plane. So that's a mu r. And then I've got these for in a moment. So I could break this up, I suppose. And I could say, well, this will be, that's alpha, and that's alpha. This will be mg sine alpha and mg cos alpha. So I'm not entirely sure exactly which direction to take at the moment, but I'm just going through some standard steps that tend to be quite useful. And what do we know? We know that we've got mu, haven't we? Which makes me think that the force diagram's correct. Let's have a go at doing our parallel and perpendicular, and perhaps something will jump out. So what have we been doing? We've been doing green typically for perpendicular. So the perpendicular situation is still going to be in equilibrium, okay? So it doesn't have to, just because things are moving down the slope, just because it's not balanced in the parallel direction, doesn't mean anything about the perpendicular. The perpendicular is separate. So for the perpendicular, we're going to say R is equal to mg cos alpha. And you might remember that cos alpha was 4/5. So I'm going to say that R is equal to 4/5 mg. Okay, And how about the parallel forces? Well, we know that it's going down the slope. So what I'm going to do is I'm going to say that mg sine alpha, because this is the force that kind of goes with the direction. And then I'm going to say minus mu r, because that's going against it. I'm going to say that's equal to ma. In fact, what I'm doing is, this is the resultant force. This is the F in F equals ma. Okay? So m is unknown. We've just been calling it little m. And a, I think that's what we're working out. Find the acceleration. Yeah. So that's just a. So this will happen in lots of questions, okay? The perpendicular won't do much very interesting, and you'll be working with the parallel. So forces down the slope take away forces acting up the slope. That's pretty much the way to do it. Now, if I start subbing some stuff in, so sine alpha was 3/5. So if I say, instead of mg sine alpha, I'm going to say 3/5 mg. Mu r, mu, did we know what mu is? Yes, it's 0.5. Okay, so that's 0.5. R is what we got from just a minute ago. So times 4/5 mg equals ma. And then I could do a little bit of cleaning up here. A half of 4/5 is 2/5. So can you see it yet? I wonder. 3/5 minus 3/5 mg minus 2 mg is equal to ma. So you end up in a situation where they've all got m in them. So it doesn't actually matter what m is, you can still work it out. You can cross all of those ones out there. So the mass is 3/5 mg take away 2g, which gives you 0.2g. Hang on a moment, I'm just checking my work. 3/5 I've got. I'm just going to check my work because I've got a slightly different answer written down here. Let's just double check. So sine was 3/5, cos was, yeah. Okay, I've dropped that one under there. That's what's happened. So 2/5 there. So yeah, it's 1/5, right? Which is 0.2g, which is equal to, not m, m's been cancelled, is equal to a. Okay, that is 2. All right, 2.0 to 1 decimal place. So that's quite an interesting result, how we cannot have the mass, but we can still work this out. So we've got the interplay now between force diagrams, F equals ma, and sometimes SUVATs, but we didn't have SUVATs just yet. In fact, that's going to be the next part, isn't it? The distance that it slides. So the distance that it slides is going to be S. And this bit here is going to mean that t equals 2. So because it's the same situation, we've just found A. So U is 0, T is 2, and S is what we want to find. So can you see that it can quickly turn into a SUVAT question? So if I use UT plus, so S equals UT plus half AT squared, I can find out what that is. And it's 3.9. So the distance from the start of the journey to the end of the journey is 3.9. In fact, the S in SUVAT equations here is quite nice. It's not as difficult as projectiles. Projectiles are difficult because they go one way and then the other. For this one, it's just going to go down the slope of this block. Okay, so you don't have to worry about change of directions and things like that. Okay, so let's do the next one while we're here as well. Okay, so we're going to have what are those features? We're going to have force diagrams, we're going to have F equals ma, we're going to have SUVAT. If we apply those tools, we should be all right. So let's just write that down. So we want force diagram, we want F equals ma, and we want SUVAT. Put those three things together and you should be good. So a particle P of mass 0.6, yeah, okay, slides with constant acceleration, So constant acceleration means there's constant forces leading to this happening. The particle passes through 2 points, A and B. Okay, so the block is on the slope here, yeah? It's going to be... So I really don't like drawing them this way around. I actually find it surprisingly difficult. So I might even redraw this. So 25. I don't think I really need to fixate on B too much. B is just the end of the journey. So it's 0.6 G. There'll be a normal reaction, won't there? 25. Okay, shall we just sort of jump in and just start doing our force diagram with this? So we've got R in the perpendicular way. We've got 0.6 G, that will be a cos 25. This will be a 0.6 G sine 25. Then we've got to keep reading. Okay. So I've got lots of information about the journey that this block is going to take. So I know, for example, the distance that we're going to be looking at is 10. The speed is the same as the velocity because we're looking in one direction here, so 2. And I've got 3.5. So I've got loads of information about that. Let's write down SUVAT and have a little think about what we've actually got in front of us here. So we've got SUVAT. We've got S equals 10 for this journey. We've got the speed at A. So we're not releasing it. It's already kind of moving. So that's 2. We've got T as 3.5. And then they just want the speed at the second part of the journey. So that's all we've got to do for that one. We don't actually need a force diagram yet. But I imagine we will need it in just a minute. So V squared equals U squared plus 2AS is going to be the way to go for that one there. So we're going to do 2 squared plus 2 lots of... Hang on a minute, why did I pick that one? That's not the one that I want. I want the one without A, which is S equals VT... Oh, hang on a minute, I've got to have a little think about this. Which one do I want? I want S equals U plus V over 2 times T. That's the one I want. So 10 equals 2 plus V over 2 times 3.5. So if I do, let's move down a little bit. So if I do 10, well, let's just do a few steps at once. So if I do 2 times 10 divided by 3.5, and then I take away the 2, that should be my V figure. So I'm dividing by the 3.5, I'm multiplying by the 2, I'm taking away that 2 to leave the V on its own. So I've got 20 in effect. 20 divided by 3.5, take away 2, gives me an exact answer of 26 over 7, which is 3.71. That makes sense because it started at 2. This is a larger number here, and it's just going to speed up as far... Well, no, yeah. It just said it's got constant acceleration, so I don't have much to go off, but that sounds about right, that 3.71. So next is find the acceleration. So I could use the V number that I've just found, but it's probably better to use a different SUVAT. So instead of this one here, what would this one be? So this is SUANT, right? So this is S equals UT plus half AT squared. That's probably the best way to do it. Okay, so let's do that one with the same numbers because it's the same journey. So that's going to be 10 equals 2 times 3.5 plus a half A, which we don't know, times by 3.5 squared. Okay, so 10 is equal to 7 plus 3.5 squared. and then half of that, so plus 49 over 8a. So take away the 7. So 10, take away 7, times it by the 8, divided by the 49. I get a is equal to 24 over 49, or 0.49. Okay, so even though I got some values from A, it's safer if I just use the same values again, because if I made a mistake with A, I wouldn't get the right answer for B, so that's why it's slightly safer for me to do it that way. Now, the more interesting bit is as follows. Find the coefficient of friction. So what we've done this time is we use SUVAT to get A, and then this is going to go backwards in the force diagram. So this question is going to get a bit much, but we're going to go SUVAT, and then the next thing we're going to do is we're going to use F equals ma, because F equals ma is the thing that links the acceleration of SUVAT and the forces of a force diagram. So if I want the coefficient of friction, I want a force diagram, don't I? So that's probably going to be the way to go. So the resultant force is going to be equal to 0.6 times 24 over 49, which is equal to, so what's that, times 0.6. The exact value, it's useful to have an exact value, it's just a little bit tidier. It's 0.29. So that's going to just sort of stay there for a second. And what I'm going to want to do now is I'm going to want to use my force diagram to find out the resultant force, which is this F here. I'm to write that down, and that should include the coefficient of friction. So like I said, there's quite a lot going on in this question. So let's just get the rest of our forces down on our force diagram before we do anything else. So that's a very basic situation. It must be a rough plane. Because it's going down and there are no forces up, that's another reason as well. We know that the friction on this diagram must be like follows. Yeah? So what we're going to say is our resultant force would be the same as 0.6 g sine 25 take away mu r. And we can do better than that because look, we've also got these forces as well. We know that r must be equal to 0.6 g cos 25. So we can sub that result in there. Okay. And then do you see that? Can you kind of see where we're going with this now? We know what the F value is, which is equal to this one here. In fact, shall I write that down? What was that? 72 over 245. We know that that's equal to that. 72 over 245. And we know that it's not just that bit there. We can sub in our value. We can sub that in and we can say mu times 0.6 g cos 25. So all you need to do from this one here is get this one here on its own, okay, to get your correct answer. So you would just take this away, take away, divide by this, change the signs, one way you could do it, okay, and you will get your mu value for that. So I'm not going to go through all those final steps there because it's just a case of checking an answer, okay. But what we want to be doing in general when the thing is moving is we want a force diagram and we want to follow all those normal steps of the force diagram. Use the perpendicular to help you with the parallel. That's what happened there. We want F equals ma. F equals ma links the force diagram and the SUVAT. So we've done the force diagram going to the SUVAT, and in this question we had the SUVAT going to the force diagram. So you need to be able to do both. It does, I'm afraid, get a little bit sort of complicated. You have to keep track of what you're doing. But if you make a habit of looking out for those three things, you should get on quite well.